Hello and welcome to Linear Regression Module 1, a bird's eye view, where we'll take a broad overview of the concept of linear regression. I'm Dr. Mark Williamson for DaCCoTA at the University of North Dakota. So what is linear regression? Well, we can think of it as modeling the relationship between a response variable and one or more predictor variables. The simplest case can be shown in a classic scatter plot where there's the y variable, which is the response, and the x variable, which is the predictor. The dots are the observations, and then this line, this best fit, shows the relationship. The equation for this sort of modeling is we have our dependent variable y, something we care about like say cancer rates, and we're trying to predict it with an independent variable, and there will be characteristics such as intercept, slope, and then of course error, because we see that these dots don't perfectly line up on the line. So really, linear regression is trying to do the same thing other analyses are doing, is trying to get the signal, say this relationship, out of the noise, the inherent messiness of the data. So let's look at the broad landscape of linear regression. Linear regression is a very big topic, but we can kind of schematize it into four kind of considerations that are pretty key: broad structure, predictor variable attributes, response variable attributes, and then other considerations. So looking at broad structure, if you have the simplest case, which we saw in the last slide, a single response, a single predictor, that's simple linear regression. Now if you add more predictor variables, that turns into multiple linear regression. And if you add multiple response variables, so multiple y's, that's multivariate linear regression. Now, turning to our predictor variable attributes, we typically think of them as numerical, but we can also have categorical variables, which change up the analysis a little bit. We can also include higher order terms, also known as polynomials. We can have fixed and random predictor variables, which need to be treated differently. And we can also have more hierarchical issues like nested predictor variables. All those things change the regression. We need to consider it. Other things that change the regression is what are response variables like. Now in the simple case, it would be normally distributed or essentially Gaussian, but that's often not the case. So we can have categorical responses, we can have count data, and even things like time to event. Those are some major differences that we can have. Then find some other considerations. Maybe we don't even want to look at the mean at all. Maybe we want to look at quantiles. Maybe there's censoring or collinearity, overfitting, or maybe we're looking at specifically time trends or other gradients like that. We can use other types of regression to account for those particularities. All right, let's take a little more look at that broad structure. We have these three basic regressions. Now we've already seen simple linear regression with a scatter plot. We're really trying to say, can we predict y with x? And mathematically what we're trying to do is find a best fit line that gets all these observations closest to that line. Now, multiple linear regression is just a extension of that, though you start not to be able to visualize it. You can still do in like 2 dimensions where you're actually trying to find the best fit plane, but in higher dimensions, while the math still works, you can't really visualize it. But that's what's still going on. Now, with multiple responses, you get into multivariate linear regression that's even more abstract. But really, with all of these, you're trying to answer these sorts of questions like, can y be predicted by x, or maybe multiple x's, or maybe multiple y's predicted by multiple x's? More concrete questions might be, can weight be predicted by height? That's simple linear. Can cancer risk be predicted by these risk factors? That's multiple. And maybe these different food sales, can they be predicted by different environmental factors? That'd be multivariate. Next, let's look at more the predictor variable attributes. So first of all, you could have in regression, typically numerical variables. We can actually include categorical as well, though you often need to recode them as sort of quasi-numerical, like level of race here. You can also add higher order terms, which adds curvature to your best fit, while remaining a linear model, because only the terms are exponential. You can also take into effect fixed and random effects. Fixed effects are sort of the default, where you have all categories of interest present in the model, like treatment groups. But then you might have a random effect where it's a subset of all possible categories. Say you look at 4 different state hospitals out of a total, whatever number there. A mixed model helps account for that, randomness. You could also have nested effects. Say you have schools you look at, but then classes within schools. Classes nested within schools, so you can use a hierarchical model to take into account that information. Next, let's look at responsive variable attributes. Now, the simplest case is if the variable is normally distributed, which follows a Gaussian distribution, though that's often not the case, so you might have to use a different distribution. Like, for example, categorical response. Say you have a yes or no on, say, a disease. Linear regression doesn't fit that very well. So you would want to use a logistical regression, which is sort of this characteristic S shape, which gives a probability of yes or no based on your X variables. And you can imagine this for more than 2 discrete categories. So that's categorical response. You can also have count data like Poisson, which would be a different distribution from the normal distribution. It's bounded by 0, and it's typically discrete, and it'll have different distributions based on that. And negative binomial quasi-Poisson are similar distributions to use. And you can also have like time to event. Survival analysis is a great example. You have time and your probability of survival. You can use something like Cox regression for that. Now, some other considerations. Perhaps you don't want to actually look at means. You actually use quantiles. It's an extension of linear regression, especially when the typical regression does not, its assumptions are not met. You can actually look at quantiles. Like median is by default the 50th quantile, but you can look at other types of quantiles, and it will still give you a lot of interesting information. Perhaps you also have censoring, which is like here's test scores, and actually the lowest is like 220, and like no score comes close in that, so we're left censored. You can actually use Tobit regression to essentially account for that censoring on one or more sides. Then also maybe you have very large models with a lot of variables, and maybe they're related to each other. That's collinearity. And adding too many variables can overfit the model. You can use a variety of regressions like ridge, lasso, elastic net, principal components. These are a lot of times used in machine learning to essentially reduce your model to get a better fit. Also, if you have things like time trends or similar gradient, it might be realistic to have actually different slopes or like different lines at different points. This is a great example here of join point, where you have different lines across time, which may be medically relevant for like prostate instance, that the rates going up here and going down here was around the time of new prostate tests. All right, so let's look at some quick examples here. SPSS is a very basic regression. We're looking at seeing if we can predict stretch length with height. So stretch looks pretty normally distributed, so we're just going to do a very basic regression. The take-home here is that height was not significant. It was greater than 0.05. We can plot it anyways, and we see that, yeah, it makes sense that this line doesn't fit the points very well. It doesn't give a lot of information. All right, let's do a little different one in R. This is based on this information from this website here, where we're actually doing a binomial, so a logistic regression, looking at seeing if the probability of defaulting on your loan can be predicted by your bank account balance. So we'll run a summary here, and what we kind of find here is actually that there's a significant relationship. This p-value is significant, and we'll use this code to plot it to show that, oh, it looks like the probability of you defaulting on your loan goes up with your bank account balance. So that's pretty interesting. And here's a more final complex model in SAS. We're actually trying to predict case fatality rate of COVID by region of the United States, so that's category. But then we have all these numerical variables that we want to, that might have an effect on case fatality rate that we're adding to our model control for it. So we can get fit. It's actually pretty good. We're using a beta distribution because it's a percentage. Here's some parameter estimates, but then the big picture takeaway is our test for fixed effects. region is significant, so there's a significant difference in at least one, and these variables were corrected for, least squared means across region, but then we can plot that to show that the case of Dakota is significantly lower in the southwest than these other regions. All right, so now we have a quick assessment. I'd suggest pausing, taking some time to fill these out yourself, and then coming back. All right, welcome back. Let's take a look. Multivariate linear regression is more than one for each of response and predictor. Polynomial regression is actually still linear because the regression coefficients are still linear. And what type of regression? Well, there's all sorts that aren't Gaussian. For example, logistic, we looked at Poisson, binomial, gamma, and the like. What type of model includes fixed and random? Fixed and random is a mixed model, you're mixing fixed and random. Fill in the blanks. Linear regression model is the relation between the response variable and one or more predictor variables. And this type of regression, well, it is either specifically join point here, but it's a more broadly thought of as piecewise regression. All right, so to conclude here, so linear regression is a really fundamental tool in statistical analysis, and we can see it's from very basic, just like a scatter plot essentially, to very sophisticated that you can't even plot. You really want to understand your data to understand what the best approach is, taking into consideration the broad structure, the response and predictor variable attributes, and other sorts of considerations. All right, well, thank you for joining me today on this bird's eye view. Tune in next time for a more detailed look in our Module 2, Leaves and Trees. Thank you.